the final topic, which is electrification of carbon capture. And this is going to be done by Professor Alan Hatton in the Department of Chemical Engineering here at MIT. Alan is, in addition to being a professor of chemical engineering, is the director of the Chemical Engineering Practice School, which gets people out into industry to learn how to use their skills in chemical engineering. Has broad interest in separations technologies, but has done some particular focus on using electrochemistry and electrochemical methods to lower costs of separations, particularly for CO2 separations in recent years. And that's led to a very interesting startup company where the CTO is Sahag Voskian. He was a PhD student, research scientist with Alan at MIT before he left not so long ago for the startup Verdox. And he will also be part of this discussion on Verdox technology and where it's going. So we'll start with Alan Hatton to talk some about the basic science and technology, and then we'll go to Dr. Voskian. Alan?
I really appreciate the opportunity to talk to you a little bit today about some of the work we've been doing. But just as an aside, I was interested to learn all about the paper industry that I spoke about just before, because the reason the practice school got started is Arthur D. Little, as a young chemical engineer, was put into the paper industry and had to take over from a German scientist that left immediately, and he had to learn how to operate the paper mills and things like that. And he realized that this was really a good way for students to learn how to work in a chemical engineering environment. And that's how he got the idea for the practice school in the first place over 100 years ago. Anyways, let me just tell you a little bit about the work that we are doing and why we're doing it. Some of the interest is because of some of the complications associated with using traditional separation techniques for carbon capture. But let's just talk about the carbon capture problem first. Obviously, we're all well aware that there's been some significant increases in the global temperature over the last few decades. It's because of the industrialization, of course, of the economy and the like. This just shows the last 60 years or so. And the reason for this can be traced to the evolution of the carbon dioxide, the release of carbon dioxide in our systems. Basically, if you look, the carbon dioxide has been increasing for the last 130, 140 years from about 300 parts per million up to over 400 parts per million nowadays. And this is really the blue line here. And the global temperature has been matching that. And we've got about a 2 degree, about a 1 degree global temperature anomaly at the moment. So clearly, there's a very strong correlation between the temperature and the CO2 in the environment. And this is, of course, a serious concern for climate change and activities. And the concern is what's going to happen in the next 50 years, 70 years or so, by the turn of the century. Just to give you an idea of the magnitude of the problem, just from emissions from fossil fuels, the global emissions are around about 37 to 40 gigatons a year of CO2 emitted, of which about around about 5 to 6 gigatons of that is related to the US emissions from coal, natural gas, and petroleum sources. If you look at the actual emissions by sector from the US fuel emissions, electricity, industry, and transportation are more or less similar, very similar in terms of the overall emissions. And it's a significant concern because these are all very heavily dependent, of course, on the fossil fuel sector at this point. If we continue looking at business as usual and continue using these fossil fuels, the CO2 emissions are anticipated to rise continuously, as shown here. And what that says is that by the time we get to the end of the century, the temperature change, the global temperature change, will be on the order of about 4 degrees. Which is unsustainable. It's really not a very comfortable position in which to be. So the goal from the IPCC and others is to reduce the CO2 emissions so we can get to a point where the temperature rise would be less than about 1.5 degrees Celsius. And typically it's around about between 2050 or 2070, we want to get down to a net zero of CO2 emissions. Now, one of the things we can do, of course, is mitigate that, but we can also reduce the use of fossil fuels. But basically, if we think about it, what's going to happen is no matter how good we are in reducing fossil fuel consumption, there's always going to be some residual fossil fuel as well. And we need to sort of get down to do some mitigation to go from this curve here down to this curve at least. And that's the area which would be mitigation. We'll talk a little bit about how we mitigate the CO2 emissions in this particular case. But then obviously what happens is we need to go below zero, so we've got to have a net negative emissions so we've got to actually remove the CO2 from the environment if we want to get to the levels where we're going to sustain the temperature below 1.5 degrees. There's a gross net negative, and the net negative is the amount that we've got to capture relative to the amount that's actually being released still by other fossil fuel sources. Which means we need negative technologies, negative emission technologies in this case. So the question is, the mitigation is what we are going to be concerned about, and I'd like to talk a little bit about that now. The strategies for CO2 mitigation and negative emissions are obviously nuclear, solar, wind, hydro, etc., all of which can generate significant amounts of the energy we needed for our various sectors, and without the problems with carbon emissions and the like. But that is not all we can do. There are other things as well that we will also need to do in the interim. And one of the biggest ones is looking at carbon capture, utilization, and storage, in which we can think about capturing the CO2 at a power plant. This is the boundary dam, that's the absorption system. This is a regeneration system for capturing of CO2. And then the question is, what do we do with the CO2 when we capture it so it does not get emitted to the environment? There is a lot of interest in looking at ways in which we might be able to use renewable resources, solar and wind, etc., to convert the CO2, reduce the CO2 back into chemicals that could have some significant value, such as chemicals, fuels, and also materials. And there's also the option, and this is very heavily looked at as well, in capturing the CO2 and then burying it in subsurface in geologic formations, saline aquifers, etc., etc. These are all looking at mitigation strategies, but as we said, we need net emissions, negative emissions technologies. And this is where bioenergy with carbon capture, direct air capture, and forestation come in, because the goal here is to remove the CO2 directly from the environment. And so a lot of what I'm going to be talking about today could feature in all of these different scenarios and could be used quite effectively in these situations. So the Carbon Capture Center its mission is to conduct cutting-edge research. And what we really want to look for is look at techno-economic assessments. We want to reduce the cost of carbon capture, enable secure carbon storage operations, and develop the carbon utilization opportunities. So we cover all of these topics as shown here. The talk about the carbon capture, utilization, and storage side of things. We obviously have a number of different considerations. We need to think about the source of the CO2, how do we go about capturing the CO2, and then how do we store the CO2 so it is no longer in the environment. Obviously, the source of CO2 comes from a number of different sectors. We have the power sector, we have transport, and we have the industrial sectors, chemicals, steel and cement, and the like. Storage of CO2, as we pointed out, it can be sequestration in saline aquifers or depleted reservoirs. It can be usefully sequestered and used in enhanced oil recovery, for instance, and also can be mineralized for construction materials and the like. And then utilization, we can either have chemical or biological utilization, actually incorporating the CO2 into useful chemical products. The question, of course, is how do we go about capturing it? That's the crucial point here, the big link, and we need to be able to capture the CO2. So what we do in a particular case is take a CO2-rich phase, an exhaust phase, and we take it to some kind of a separation unit, some absorber. It can either be an absorption or an adsorption type process. And we remove the CO2 from that exhaust stream and have a CO2 lean stream leaving. Obviously, the absorber only has a finite capacity for the CO2. At some point, it gets fully loaded, and we have to take it then to regenerate it or release the CO2. So we take the CO2-rich sorbent and take it to a desorber, where we put in some kind of regeneration energy. It can be a number of different ways we can do this. We can then desorb the material, break the bonds, get the CO2 coming off of the pure CO2 product that can then be used for whatever application we need. And once we've done that, we have the sorbent itself is now lean of CO2. It's been depleted of CO2 and can be reset back to the sorber system. So how do we go about doing this? Well, there are a number of different approaches. There's a temperature swing. There's which the energy there is temperature changes to break any chemical bonds that might be there. There's pressure changes to change the overall thermodynamic driving force between the sorbent and the sweep stream. And then what I'd like to talk about today is a little bit more of the electrochemical potential swing approach. And I'll spend some time discussing that and then hand over to Sahag, who will talk about the latest technology we've been looking at. So just to give an example of a typical process, this is the benchmark process that they use for amine, for CO2 capture, in which we have an absorber like this, in which we contact the amine or the CO2 stream with an amine in aqueous solution. This amine will complex with the CO2 to form this carbamate as shown here. And once it's fully loaded, we can then take it back and send it to a second absorption column. This case, we'd actually heat it up to about 120 degrees, break this chemical bond, and release the CO2 and regenerate the amine that can then be circulated back, cooled down again, and sent back to the absorption column, where it can go through the whole cycle again. This just shows you the boundary dam one. We've got the strong absorber here and the stripper section of the desorber over there to give you an idea of the scale of this facility. Now the question is, this is quite energy intensive. It needs a lot of steam. And where do we get the steam? If you're looking at power plants and the like, we're taking them directly from looking at the steam cycle, which can disrupt the steam cycle, expensive retrofitting, and so on. It also has significant degradation of the overall derating of the overall power plant. The other issue associated with these high temperatures in terms of corrosion, in terms of loss of degradation, in terms of loss of these amines because of evaporation, and so on, etc. So we were wondering, are there other ways in which we might be able to do this, where we can actually have a standalone unit that we can just plug into some kind of power source, electrical power source, that can then do the similar kind of activity, but without the complexity of the thermal regeneration schemes. Can also keep it at ambient conditions, so we minimize the degradation of the solvents, and lots of other application opportunities as well. The question is, how do we go about doing this? So we've got two different types of approaches generically for electrochemically mediated CO2 capture and release. What we're relying on here is the electrochemical redox activity of chemicals and how we can actually change the oxidation reduction states and oxidation reduced states. So typically we'd have a case where we've got a sorbent as shown here. The CO2 would be captured as indicated to form some kind of a complex. We then go through a release stage. In this particular case, what we do is we take some displacer, and I'll talk about a couple of different ones later, that we then reduce, oxidize. And when we oxidize the displacer, it will just interact much more strongly with the sorbent than does the CO2, and it displaces the CO2 off like that, and that's what we can do. So what we were using before with the amine systems was using heat. We are now using this electrochemically generated displacer. And then we got to regenerate it. We come by and we can, by oxidizing this again, by reducing it again, we then can pull off this displacer and form the reduced species again and regenerate the compound. The other approach we can look at is activated capture and release, in which we have a reduced sorbent as shown here, the capture and the like, and we can then go through, and the sorbent itself is now the electrochemically active species, as opposed to this case the displacer was. There's now electrochemically active species, so we can actually reduce or oxidize the adsorbent in this particular case and release the CO2. And then what we can do is regenerate it by reducing it again and bring it back into the reduced sorbent back to the capture zone. So these are two different types of approaches we've been looking at. I'll talk about the displacement release, and Sahag will talk a little bit about the activated capture release process. The actual displacement release is shown here for the CO2 absorption column. We got CO2 complexing with the amines in the absorption column. We then take that to an anode chamber in an electrochemical cell. An electrochemical cell is shown here, where we oxidize the electrode, oxidize the copper, send the copper out. It will displace the CO2, interact with the amines as shown here. The displaced CO2 is released in a flash tank, and we take that then back to the cathode chamber, where we now plate out the copper, we reduce the copper, and we free up the amines to go back in the cycle. This particular process works rather effectively. This is an example of the equipment. I'm not going to describe that in detail. This is the actual electrochemical desorption unit that we've been working with. This just shows you how this works in general, that the CO2 output that we have from the desorption unit is shown here. The green is the applied current, and the amount of CO2 we release is directly related to the applied current as shown here. And this is because the applied current determines the rate at which we add the copper ions to the solution, and therefore the rate at which we can release the CO2. This just shows the stability of operation over many, many different cycles. Thermodynamically, we can go through the whole process thermodynamically and set up a thermodynamic diagram showing the actual potential versus the amount of copper that's been released into the system or reduced as we go through the whole cycle. And the general energy associated with this is given by the area under this curve. And if we show what's happened here is that we are, in our overall work for the system electrochemically, this is the amount of work that we would need in the system. And it's pretty reasonable in terms of the general overall work that other folk have been seeing. The costs, the capture costs of something like this are also are not exorbitant. In this particular case, if we look at the CO2 capture cost in dollars per ton, providing the membrane separated in the cell is not too pricey, we can get the capture cost down to about $40 a ton by having a certain working capacity in the overall system. I think the take-home message here is that this is a very viable process. It has good opportunities for both cost reduction, simplicity of operation, and also non-thermal amines. Another place we can look at is using electrochemical modulation, pH modulation, which we can go through a system where we take a carbonate solution at a high pH, absorb CO2, it lowers the pH to get a bicarbonate. And then if we add protons to even lower the pH further, we then release the CO2 and we get in this particular region. We release the CO2 and come back here, and we can now increase the pH again by removing the protons to give us the carbonate solution again and go through this cycle. So the question here is not copper ions we're adding, but protons here that we're adding to the system for the capture and release stages. And the way we do this in this particular case is using manganese dioxide electrodes, and they work very effectively. This is again the kind of process we're looking at. The absorption system and the regeneration system, very much like the other one I talked about with the copper, except now we're looking at proton transfer through here. And this works very effectively. This is the CO2 loading as a function of the proton added to the system. And we can see as we increase the pH or increase the proton added to the system, we reduce the CO2 loading quite significantly. The pH itself actually remains quite constant during this process until right near the end, which was interesting. The important part is that, again, that the electrochemical work that we would need in a case like this is pretty close to around about 35 kilojoules per mole. Of course, we've got to add compression costs and things like that to that. So just in summary then, these electrochemically mediated CO2 displacement, the advantages are they do not need steam or extensive retrofitting. They're isothermal, low temperature operation. They can desorb at pressure. We utilize low-grade waste heat to improve efficiency, and the competitive cost and energy requirements seem to be an advantage of these systems. So let me go on briefly to talk about the other process, electrochemically mediated CO2 capture and release, in which it's not the component we add into the system to displace the CO2 that is the electrochemically active species, but the actual adsorbent itself is electrochemically active. And as we talked about earlier. This is one example, and this is something Sahag will discuss in a little bit more detail very soon. If we take this particular compound, like a benzoquinone and lots of others, we take this, it's fairly neutral. It doesn't have any real interesting features until we reduce it, and we get a very strong electronic density on the oxygens over here. This is an activated state now. An electrophile like CO2 will come in, react to form this dicarbonate system as shown in this particular case, and we can then regenerate this by oxidizing again in another section, oxidizing it, regenerate the compound. The CO2 now has no affinity for the quinone, and the quinone is then released. So we can go through this particular cycle. So this is different from what we talked about before, but I think it gives you some idea of the advantages one might have here. It's a little less complicated in some respects. This can be done in a number of different ways. One can use liquid membrane facilitated transport, in which at the cathode we do the reduction, CO2 through gas diffusion electrode, CO2 diffusion diffuses in complexes, moves across to the anode chamber where it gets released again. This can be done either in a liquid membrane type approach, or can also be done in the flow system. The other approaches that can be used as well, and this is looking at electroswing adsorption, when instead of having a fluid stream, a liquid stream like that, we actually have adsorbents that are based on these quinone type materials. And this is really what I want Sahag to go in and talk about in a couple of minutes. I just would like to just acknowledge before we get finished that these are the students and postdocs that have been working on this work, on this job, and these are the funding sources we've had over the last few years. So I'd like to hand over to Sahag, who can tell you how we've been taking some of our technologies and looking to exploiting these in a real world environment in terms of our startup, Verdox.
Thank you, Professor, for the introduction. I'd like to now talk a bit more about what we're doing at Verdox. It's a company that we've recently started in October 2019, along with Professor Hatton and Brian Baines. Here, what we're trying to do is look more into the solid state version of the quinone system that Professor Hatton talked about. So we talked a bit about the quinone chemistry, and we showed that quinones are very interesting electrochemical molecules in that they could be electrochemically activated to react with CO2. But one interesting point here is that quinones have binary affinity to CO2. They either are binding with it until saturation and complete usage of the quinone molecule, or they have zero affinity to it. And this binary affinity could be toggled electrochemically by reversing the polarity. So now imagine a number of molecules immobilized onto a surface, and here the surface is an electrode of an electrochemical cell, or a battery, if you will, that is about 1 to 2 millimeters thick. And you have these sheets of electrochemical cells that are exposed to CO2 flow. Upon activation of these electrodes by charging the electrochemical cell, quinone switches from 0 affinity to CO2 to 100% affinity and reacts with the CO2 that's in the carrier stream until all the quinone sites are saturated. So this could be done either at 10%, 10 to 15% CO2, which is what you typically find in exhaust streams, or at 400 ppm in air. So the same utility and utilization of quinone is achieved regardless of the concentration of the stream. And this is a unique thermodynamic feature of this process. And likewise, upon reversing the polarity, this affinity is completely reversed or neutralized, such that all the CO2 is released regardless of the environment of the electrochemical cell. So now you can imagine a process where you're capturing pure CO2 from 400 ppm and releasing it into a carrier stream that is 100% CO2. So in this process, you're maximizing the percent recovery of CO2 from your inlet stream, and you're minimizing or you're also maximizing the purity of the stream. Now, the way we achieve this is by immobilizing these quinone molecules and some other counter molecules onto these electrodes and stack them in a unit that looks like this, where you have parallel sheets that operate in this environment of electrochemical capture and release. So here I'll show some micrographs of what these electrodes look like. You'll see here that we have a fiber cloth that has coated and uncoated parts. Here you can see the uncoated carbon fibers, and here is a coated part that is, upon further magnification, is a composite of polymer and carbonaceous material that provide large surface area and high conductivity to these quinone units so that they can be easily accessed equally well by electrons, electrolyte, and carbon dioxide that's in the environment of these electrodes. Here I'd like to show a quick animation of how how a unit using these electrodes and electrochemical cells would operate. So imagine you have these absorption module, as you can see here, that has a stack of electrochemical cells comprised of the quinone active electrodes, the separators, and some counter electrode to complete the charge or balance the charge. And these electrochemical cells could be stacked in parallel to trace gas flow channels, where a feed of some mixture of CO2 and other gases is brought in. And upon the electrochemical activation of these cells by charging them, the quinone on the electrodes is activated, and it has high affinity to CO2 now, and the reaction proceeds until all the quinone sites are occupied. And at the process level, you can see that here we're bringing in a feed and only pure nitrogen leaves while the CO2 gets trapped onto these electrodes, much like in a pressure swing or temperature swing adsorption step. And likewise, during release, we reverse the polarity, and now this pure CO2 can be released into the gas flow channels for downstream usage and valorization. And the interesting part is that most carbon capture technologies have the energetic step, the release being the energetic step. While in our system, we have the charging or the activation of the quinone as the energetic step, which happens around capture time. So the experimental results that we had in this sealed chamber, first you can see here the electrodes that we assembled and put them in this sealed chamber that was charged with gas, either pure gas or different concentrations. The experimental results that we got show that we are utilizing a good portion of the quinone, up to 70%, and we're capturing and releasing gas, as you can see here by the fluctuations of the pressure in the chamber, in the sealed chamber. And this is very synchronized with the charge-discharge of the electrochemical cell. And we run this over multiple cycles, and we see that we sustain or retain up to 70% of the capacity even after 7,000 cycles of capture and release, which is a very high number. But what we're trying here at Verdox is push this number by half to one order of magnitude to make the process more economically viable and increase the cycle time and the cycle life and calendar life of these electrochemical cells. These experiments show that we utilize more than 70% of the quinone, like I said earlier, and we show that we capture carbon dioxide at 40 to 50 kilojoules per mole energetic expenditure, which is very competitive with other carbon capture technologies, and it's at 90% Faraday efficiency. But the interesting part is that most carbon capture technologies start having their second law efficiency decrease dramatically as the concentration of the inlet decreases. In our case, our second law efficiency is constant and is dictated by the electrochemistry of the cell, which in itself is somewhat independent of the carbon dioxide concentration. So we can maintain this high efficiency and low energetic consumption at even much lower concentrations of carbon dioxide, where many other incumbent technologies become economically not very feasible. Here I'll show some more results. These were done in a more realistic environment where there's flow across a set of parallel electrodes like the one you saw in the animation. And you can see that we have a CO2-rich feed stream coming in, but the outlet is being depleted of the CO2 because their CO2 is getting trapped onto the electrodes via chemical binding to quinone sites. And here in this experiment, you see that we ran the experiment over a range of gas concentrations or feed gas concentrations, and we achieved early saturation with higher 2% here compared to 0.6% because the electrodes were saturated sooner with the higher concentration feed. But upon normalizing these profiles with the inlet concentration, you see that all the curves superimpose and trace this trapezoidal area. And this is a sign that, or this is an indication that the electrodes behave independent of the inlet concentration, and their capacity is not an equilibrium capacity. It is the same regardless of inlet concentration. In another system here that is much bigger, we show the capture of 10% CO2, up to 10 bed volumes of gas has been treated, which shows that up to 1 pure bed volume of gas has been absorbed onto the electrodes. In another system that was smaller, we treat CO2 at 8,000 ppms, which is on the order of magnitude of indoor air, or air that we breathe inside sealed buildings. And we can show consistent behavior here over multiple runs where the electrodes are being saturated after a certain volume of gas has been treated. Now, coming to the release, I'm not going to delve too much into this, but you can, much like in a pressure swing or temperature swing operation, you can limit the working capacity and do an optimization of the energy expenditure versus the amount of bed utilized. But at a high level, conceptual level, thermodynamically, if you look at typical sorbent material, they usually have isotherms that look something similar to this. And these isotherms indicate the amount of material, or CO2 in this case, that could be absorbed per mass of sorbent. And by toggling the temperature, it is possible to switch from certain high quantity of CO2 absorbed to lower quantity, and this will be the working capacity. Of course, there's variation here of the amount that could be absorbed based on the partial pressure or the concentration that the sorbent material is exposed to. Likewise, in pressure swing operations, there's variability, and this needs to be achieved by changing the partial pressure of CO2. This is usually done by exposing the sorbent either to vacuum or steam. In our system, in electroswing adsorption, we have what we call rectangular equilibria, or isovolts, if you will, where at some level of activation of the electrode, we have full capacity of the electrode utilized regardless of the partial pressure or the concentration. And upon deactivation, there is zero capacity for these electrodes. It's not a typical equilibrium isotherm. And this is what makes the concept and technology very unique.
Sahag, could you wrap up, because we're just out of time now?
Sure, absolutely.
Okay, thank you.
So one thing I would like to show here is that we built this prototype here at MIT, and our modules that we're developing at Verdox are conceptually similar to this. And as far as applications are concerned, you can imagine a number of these beds operating in parallel, where the feed could be anything from air, shipping exhaust, industrial exhaust, and downstream applications could be either CO2 enrichment in greenhouses, algae ponds, and so on, enhanced oil recovery by sequestration and pressurization, or valorization to chemicals and fuels. And here we go into more detail, but I'm going to skip this. But as a summary, there are early markets that could be penetrated, like beverage and cold suppliers and CO2 enrichment, as well as indoor ventilation. And the future markets involve the large-scale direct air capture and mobile capture of CO2. The founding team is Dr. Brian Baines as the CEO, who's also an alumnus of the department, myself, and Professor Hatton. With that, I'd like to thank you for your attention and time.
Very interesting presentation, and in fact, a very interesting set of 3 presentations covering how we could make dispatchable energy for the future that's zero carbon, how we can use less energy in the future, and how we can get rid of some of the CO2 that's been put in the atmosphere in excess. So very important contributions. I'm afraid we are out of time for the session, so we're going to have to skip the questions here. I thank you all the participants for taking part. I thank ILP for its doing the organization. And with that, I'd like to turn it back to CJ and see if you have any closing remarks.
Thanks to our speakers, and obviously thank you for all the participants around the world. So this concludes our second session of the Energy Innovation webinar. We'll offer the third session next week, next Thursday, May 21st, starting at 10 a.m. I look forward to seeing you next week. Have a good day and good night. Bye.